Now, in this video, we're going to look at a discrete distribution that we can't really do calculus on, but we can do it sort of numerically to solve for our maximum likelihood function. So in the previous maximum likelihood function video, we talked about setting up an exponential distribution and a binomial distribution, either the binomial or the negative binomial examples. And then we hinted at how with one variable calculus, you can go about solving for these functions. So what we're going to do in this video is we're going to set up a hypergeometric example, and then we're going to look at how to solve them. We're going to have graphs where we can look at them numerically, because for the hypergeometric example, that's really the only way that you can do this. But then we will also discuss the actual calculus of doing the solving for zero, but with the graph in mind. Okay, so maximum likelihood function. So to set up the maximum likelihood function, remember, we have a series of outcomes, and the hypergeometric function in particular, the distribution, is already a calculation based on a series of outcomes. So it's one of those cases where the maximum likelihood function is itself just the distribution with the values filled in. So it's, in that sense, it's similar to the binomial and negative binomial distributions and less similar to the exponential distributions. But we have a collection of 1,000 samples, let's say, and they're in two types, and that's how it's a finite sample, a finite population. We have two discrete types. This is how we know that it's hypergeometric. And we want to estimate the number of type A items in the entire collection without having to literally count all 1,000 items. So after collecting 20 samples, we end up with 8 samples of type A. And so we fill in the values for the hypergeometric distribution for the things that we know, which is the total size of the collection, which is 1,000. We know the sample size that we took here was 20, and we know the number of type A that we got out of the distribution, which was 8. And so our hypergeometric distribution looks like this. This is the maximum likelihood function, because again, remember, the hypergeometric distribution is defined initially by, it is a collection of events. It is not like the exponential distribution, the time between this event and the next one stop. This is I've taken something out, and I've taken something else out, and I've taken something else. So there's multiple events already buried in this function. And so we don't have to do that multiplication because it's already built in to this particular scenario. So again, this is one of the reasons why I disliked using the binomial distribution as a sort of base example, because it works out a little differently, because the binomial distribution is already a collection of multiple events. And that is deceptive relative to other examples. Okay, so what we want to do, we have our, from the previous video, we have our two maximum likelihood functions that we've derived previously, and we have this hypergeometric example, and we want to actually go ahead and find the most likely outcomes for our missing parameters. We will return to the normal distribution example in video number 3. All right, so let us return to the first example we discussed in the previous video, how to calculate our maximum likelihood estimate for our parameter. In that case, we had a nice, smooth, continuous function based on our exponential distribution, which we found to be lambda to the 10 because we had 10 observations, and e to the negative 30 lambda. Negative 30, you may recall, was the sum of our observation, or 30 was the sum of our observations. So maximum likelihood estimate, it's just calc 1. We want to find the most likely value of lambda. Where is that a peak? relative to these outcomes that we've obtained. So we take the derivative with respect to lambda, and then we set it equal to 0. So this is a product rule. So 10 comes down, we reduce the power by 9, we copy the second function. In this case, we take the derivative of the second function. The negative 30 comes down, so changing that to a minus instead of a plus. Lambda to the 10 stays. And then we set that equal to 0. I'm going to factor out as much as I possibly can. I can factor a 10 out. I can factor lambda to the 9th out, since that's the smaller exponent. And I have an e to the negative 30 lambda on both terms. I factor that out. And I'm left with this thing, which, I mean, this could be 0 if lambda was equal to 0. But again, that's a minimum, not a maximum. And then I have this other expression in terms of lambda. That's the thing that I want to set equal to 0. And that gives me lambda, my estimate for lambda based on these observations is 1/3. Now, the relationship between the exponential distribution and the parameter lambda is that it's the reciprocal of the mean. And if you take the mean of our observations, they summed up to 30, we divide by 10, the mean is 3. And so this is consistent with the mean being 1 over lambda. If lambda is 1/3, our mean is 3. Again, that's a method of moments approach, but it is our answer for the MLE is consistent with that. And again, we can look at this graphically. Our minimum likelihood is 0, is down here at 0. Again, it approaches 0 on the other side. It never really gets to 0, of course, because it's an exponential function. But in the middle, our 1/3, that's where our peak is. So this is the graph of our maximum likelihood function. And where is the probability highest? The probability for all of these outcomes is highest when lambda is equal to 1/3. Same thing for the function that we talked about. The second one that we set up last time, this was our binomial example. We ended up with our maximum likelihood function being p to the 20, 1 minus p to the 10. And if we take that derivative with respect to p, because that's what we want to find the maximum value of, where is this probability maximum? Again, product rule, bring down the 20, make that 19, copy the second function. And then when we do the derivative of 1 minus p to the 10, the 10 comes down, we make this 1 minus p to the 9, but the chain rule gives us that minus sign. If you're getting, if you miss this minus sign and you make a mistake and you get a probability that is negative, remember that's not allowed. That's a sign of a sign error. What can I pull out of this in order to simplify this? Well, p to the 19th can come out. 1 minus p to the 9 can come out. And I can pull out a 10 because this is 20 and 10. Sometimes you can't always pull out some of these constant factors, but that's fine. But what am I left with? I'm left with, since I pulled out only 9 of these, I'm left with a 1 minus p and a 2. And then this one, I pulled out all of these 1 minus p's, and I was just left with 1 p left over. And again, I set that equal to 0. 0 and 1 are not possible values because they give me a probability of 0. So those are minima. And then I just pull this out, I distribute, and I end up with p is 2/3. And so again, we look at the graph. Again, this is the graph of our p to the 20, 1 minus p to the 10 function, the original maximum likelihood function. The scale here is very, very small, because if you take a fraction and you raise it to the 20th power, you're going to get a very, very, very teeny tiny function. But the where this peak is what I care about, not what the value of it is at that point. So you can see that, again, this does line up with 2/3. Now that's if you can do the calculus. But when you have combination formulas like this, factorials and things like that, even if we were to translate this into factorials, we would not really be able to do the calculus, because we would have to convert it into something fancy like a gamma function or a approximation for the exponential, which for the factorial using exponentials, which really only works for really big numbers, and that wouldn't necessarily fly here. So instead, what we can do is we can actually do this numerically. We know that M has to be restricted between values of 0 and 1,000 because there's only 1,000 in the population. Our combination formula can't have this be negative. So in fact, we also know that in fact, M can't be smaller than 12 because, or than 8, because this would not make any sense if M was 4, because the larger number always has to be bigger. So we actually know there's actually a finite range of values that we have to consider for the hypergeometric distribution. And so we can easily set up an example where we test all the possible values between 8 and a minimum of 8 for this side and a maximum of 988, because 988 would make this 12 over 12. And then we just test all the values, and then we can plot them and see where our peak is going. And so I did this calculation in Excel. This is the graph that I obtained by, again, plotting the outcomes of my hypergeometric maximum likelihood function anywhere from 8 to 988. And we can see we get a peak, looks like around 404 and change. And in fact, if you look at the table of the calculations, you can find the exact location, not from the graph, just kind of helps you narrow it down, but you can see the exact value where you get the maximum value for this function. And the maximum, again, the outcome of this function is itself not that important. It's where the maximum is. And you can see that at 400, that value is a little bit bigger than 401 or 399. And so this is M equals 400 is the maximum likelihood in terms of there being 400 of type A in the sample versus having to count all of them given the sample size that they took. So again, you would have to do basically the same strategy if you were doing something like the Poisson distribution. You would want to evaluate it and numerically in order to get around that factorial component, and then pick out where the maximum is from those numerical calculations. And again, you can do that if you have a nice continuous function. You can still do that calculation, but it's more difficult, particularly when you have decimals. You would have to keep sort of zooming in until you were sure you had the right value. If you do the calculus, then it will get you the exact value without you having to do approximations. And then you're free to use the graph, of course, to estimate, to sort of confirm the algebra that you got to make sure that your answer agrees with your graph. That's a good way to double check to make sure that you haven't made any calculation errors, or dropped a sign or done something weird like that. All right, so in the next video, we're going to look at the two-dimensional case of the normal distribution, and then we'll set up the function and we'll go through all of the calculations. This next example is the thing that basically broke my Word document 3 times. So